Greetings and welcome, friends. We were talking yesterday about solving right triangles, and in many of the cases, from this section anyway, we were talking about when we have two sides or a ratio, and I'm looking for an angle, how would we do that? And our solution ended up being related to the trigonometric inverses, such as sine inverse, cosine inverse, tan inverse, and by the way, just so you know, that's not the only way that those are written. Sine inverse of a ratio will give you an angle. The same concept can be written like this: arc sine, all right, of a ratio. All right, those are synonymous with one another. So just so you guys realize that in advance. But let's take a look at problem 19. This is on page 309. Yep. And they asked us to figure out all values of x between 0 and 360 for which sine is equal to the negative square root of 2 over 2. So the way we figured this out yesterday, we talked about, first of all, let's figure out what quadrants sine is negative in, and that's going to be in quadrant 3 and 4. So I know that whatever I get, that I'm going to really only have the reference angle from this, and then I'll have to figure out what the actual angles are. All right. So, so my question is, for what angle of sine do you get the square root of 2 over 2? And we could use the hand trick to figure that out, where I'd put down my 45-degree finger and I'd realize I got the square root of 2 over 2. So I'd get 45 degrees using my hand trick. So I know that my reference angle is 45 degrees. All right. And now to figure out the actual angles for these, well, I'd need to find that angle and this angle, right, are the two that I'm looking for. So I'm going to get x equals, well, this is 180 plus 45, so that's 225 degrees. And this is going to be 270 plus 45, or 360 minus 45, so that's going to be 315 degrees. Now, if I wanted to solve this more algebraically, I just want to point out that sometimes this can be a little bit tricky to do on a calculator. But to get x by itself, we could sine inverse both sides. All right, is the idea. And I'm interested to see what our calculator says x is in this case. I believe it's going to give me an answer between negative 90 and positive 90. And let's see if I can show you guys this, if it'll focus. So I plugged in a sine inverse of negative root 2 over 2, and I got negative 45 degrees. All right. So sine inverse of negative root 2 over 2, it told me negative 45 degrees. However, that's not the whole story. That's technically coterminal with this angle here. So that would give me one of my answers, but it wouldn't have given me both of my answers. All right. So I just want to point out that you still have to be clever enough to use the calculator as a tool, but the calculator is not going to give you everything. All right, so if I got x equals negative 45, well, adding 360 to that would give me the 315 degrees, and that still wouldn't have given me both of my answers. I'd also have to realize that sine is negative in this other quadrant, and that I could then, you know, be able to use this in some way of a reference angle, so to speak, if I think about it that way. And try to figure out the other solution, the 225, that way. So I just want to point out, you still have to be kind of smarter than your calculator. The sine inverse and cosine inverse and tangent inverse functions, they usually have a restricted range. If I recall, I believe sine and tangent will only give you angles, or sine inverse and tan inverse will typically give you angles between here and here. For the fourth or first quadrant, and cosine inverse will typically only give you the angle from here to here in first or second quadrant. We'll talk more about that later as we cover different chapters and zones, but I want to point out that we technically could solve this problem using only our hand tricks and recalling what quadrants we are positive or negative in. So let's take a look at problem 23. It's asking us to just simplify this. And what I want to point out is Remember tan inverse, all right? What does tan inverse take as an input? It takes in a ratio, and what does it give as an output? Right? It's going to give an angle, all right? So tan inverse of 2/3 is going to give me an angle, and now tangent of that angle is going to give me a ratio. And it would make sense in this case if tan inverse of the ratio 2/3 gives me an angle, that tan of that angle would give me the same exact ratio of 2/3. All right. The other way you could view this is kind of the tan and the tan inverse are just canceling each other out and leaving the 2/3. But I wanted to at least kind of have us analyze the domain and range agreement there, so to speak, that we have going on. Actually, I might want to, did we do question 27? I'm going to add this to it right here. This is cosine of sine inverse of 2/5. Okay, so check this out. This is sine inverse of 2/5. So that's going to give me an angle, all right, for which the opposite over hypotenuse is 2/5. And if I want cosine of that angle, that's not going to give me the ratio of opposite to hypotenuse. Cosine would give me the ratio of what to what? Adjacent to hypotenuse. So I've got to figure out if my triangle, I mean, you could actually literally draw a picture for this if you want. Just trying to make as many different connections as possible is probably a good thing. So I have some angle theta, and I know that the opposite is 2 and the hypotenuse is 5, or at least their ratio is reduced to a 2/5 ratio. So if I want to then figure out the cosine of this same angle, all right, I'm going to have to figure out what the adjacent is. How could I find the adjacent? Well, I could use Pythagorean theorem, right? This adjacent squared plus 2 squared equals 5 squared. And I get a squared plus 4 equals 25. A squared equals the square root of 21. And then a equals the square root of 21. Technically plus or minus, but I'm only concerned with the positive since this is a geometric concept right here. So if a is the square root of 21, what is the cosine of this angle theta? Yeah, adjacent over hypotenuse, so that's going to equal the square root of 21 over 5. Now actually I'm interested to see what happens if we did plug this in a calculator. Well, first of all, it's not going to give us the square root of 21 over 5. But let's see. So sine inverse of 2/5. All right. So the actual angle measure is 23.58 degrees. So this angle is 23.58 degrees. All right. And now if I take the cosine of that angle, so if I do cosine of second answer, I get 0.9165. Now, I'm claiming that that is the same as the square root of 21 divided by 5. Oh, that is not what I mean. Right? I do not want that under the radical. So I'd have to move over here. I hit the over arrow in order to get out from underneath that radical. Divided by 5, and notice I do in fact get the same value. So if you used only a calculator for this, you probably only would have gotten a decimal approximation and not the exact value. But I just want to point out that, you know, through drawing pictures, understanding these relationships, we actually could you know, figure this out exactly if we wanted to. All right, and just realizing that sine inverse of the ratio is giving me an angle, cosine of that same angle, well, I would just need the other side of that triangle. So all sorts of good stuff there. So let's look at the last question. 31. So they gave us a picture of a triangle. Let's see. I'll just redraw it here. Yes, bless you. Wobbly triangle. That's fine, though. So it's triangle MNP. Mathematicians usually don't use O for stuff because it looks like 0. Although I have seen O used as a variable name to represent the center of a circle, but I don't know. So let's see, then we'd have, in our case, I was told little m is 14.3, so that would be the side opposite capital M angle, and little n is 18.8. So they want us to find out what is angle n. All right. So for this situation, what is 18.8 from this angle's perspective? Opposite, and this is the adjacent, so what trig ratio am I interested in? Tangent. So I'm going to say tan of theta, or tan n, right, is going to equal 18.8 divided by 14.3. Tangent is one of the ratio, or is, yeah, I guess one of the ratios, if you include the reciprocal ones, that can be bigger than 1. All right, sine and cosine cannot be. So if I tan inverse both sides, tanverse, Danny Tanner, this problem here, we've got n, cap n is equal to that, so I'm going to hit in my calculator second tan inverse, 18.8 divided by 14.3, close parentheses, and I get n is equal to 52.74 degrees. All right, and that is what the book has as its answer as well. Well, they rounded to the 10th, and that's what the directions said. Now, what if I want to find angle M? What could you do to find angle M? Yeah, I could subtract these two from 180, or I could just do 90 minus angle N. So I'm going to get M equals, I'll just, on my calculator, do 90 minus second ants, and I'll get 37.25, or 26, I guess I'll round up, degrees. So there's angle M. And if I want to just solve this triangle the whole way, why not? Let's do this, even though we didn't have to last night. How could I find side P? I could Pythagorean theorem, because I was given those two values. That would be the most guaranteed way to do it, since I wouldn't have to worry about possibly infecting it with a previously wrongly calculated answer from the angle. If I wanted to use angle n's perspective to do it, I could have used sine and compared this to that. It should equal the sine of my angle, 52.74. I could have used cosine of this to that, would equal the cosine of this angle, and end up, you know, solving it that way. But you also could just do Pythagorean theorem just as easily. So I would just do 18.8 squared plus 14.3 squared equals little p squared. So I'll square that, plus 14.3 squared. So I get, not 1, 557.93 is equal to p squared. And then I just square both sides, and I'd get little p is equal to square root of that. So that's 23.62. All right, so I just want to point out that now we actually have the ability of solving triangles when given, right triangles specifically, when given 3 pieces of information about them, one of them being the right angle. Now, there's a situation where we would not be able to solve the triangle when given 3 pieces of information. All right? I just want to point out we are able to solve triangles when I'm given an angle, angle and a side, all right, one of them being a right angle. I can do it with an angle and 2 sides, which I'm not going to write out, right? We can do it with side, 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 all right? Or side, yeah. Well, I already know it's a right angle in the Pythagorean theorem. That's kind of this situation. These are both grouped. The situation that we can't do is angle, angle, angle. Why couldn't I solve that triangle?
Because you need a different kind of opposite. You need like a number.
Well, what if I told you I have a 30, 60, 90? Tell me the length of the sides. Well, isn't 30 and 60, those are numbers?
The angle could go either 100 feet or 1 foot.
Right. So the idea is that I could have a small triangle that's 30, 60, 90. I could have a big triangle that's 30, 60, 90. Right. Because of similar triangles, I couldn't actually find the side lengths. I could tell you the ratios of those side lengths, but I wouldn't be able to tell you how big the triangle was. So being able to, it's interesting that with all three sides, you could actually figure out, the angles, but with all angles, we can't figure out the sides. So just wanted to point that out. So anyways, thanks for watching, Internet friends. Bye-bye.